All right, the first lesson after spring break. All right, so bearing with me, guys. This is all kind of new to me. I'm using sort of new technology on my tablet and all that kind of stuff. So bear with it. All right, hopefully it'll all work out for everybody. All right, but keep that in mind. This is new to everybody. All right, so the first set of notes that we're going to look at is the 4.4 application. So application space E and functions. So remember, before we went off on a break, we learned derivatives of exponentials and logarithms. And if I have time, I might post a video kind of going back and reviewing those as well, since it's been a couple of weeks since we did that. All right, but right now we're going to get into the next set of notes, which the next set of notes are applications of exponentials. Now, these are addition to what we talked about before we went on break. We did finding critical values, max and mins, increase, decrease, tangent lines. Again, we did applications of all of those before we went on break. And so we're just going to add to these in the next section. All right, so we're going to look at different types of functions that show up in applications. All right, so the first one we're going to look at is an application of revenue. All right, so I have a unit selling price in dollars for a quantity demanded, so it's in dollars for a quantity X of whatever this item represents. And so we're given the price demand function. And what makes this different from what we did before is previously our price demand functions were always linear. This one is obviously not linear. It's an exponential function. All right, so we've got a price of our certain item, which is 250 times that e to the negative 0025x over a domain 0 to 800. And so that's a closed domain. All right, closed domain because I include 0 and I include 800 because it's brackets. Again, bear with my handwriting because this is all on a tablet and my handwriting was already messy enough before I started writing on tablets. All right, I digress. All right, the first question we're going to ask is find the revenue. All right, again, find the revenue is not new. Revenue is still price times quantity. The new part is the price equation is not linear. All right, so our price equation is 250 e raised to the negative 0.025 times another x. Again, not new. Price demand times x. Right, new part again is that it's an e instead of a line. Right, I am going to rewrite it just to make, I know I'm going to find a derivative because we're going to optimize. So to make life a little easier, I'm going to move the x in and multiply it by the 250, and I'm allowed to do that, right? I can rearrange multiplication. 3 times 2 is exactly the same as 2 times 3, and so that's the principle I'm using. All right, so my revenue equation that I'll be using is 250 times x times that e term. All right, so there's part A. Now part B, find the number of items. So how many items do we need to sell in order to optimize revenue? Well, optimize revenue means I want to maximize revenue, right? Revenue is sales. I want to maximize my sales. And so for part B, since it's the closed domain, we're going to find any critical value on the given domain and then use the extreme value theorem to solve for which one's the smallest. All right, so first, find my critical values, which means I need my derivative and set it equal to 0. All right, so derivative first. All right, so the derivative, I am going to have to use two rules. I've got the 250x times that e term. So 250x is a function times the e function. So product rule. And then on the e, since it's something other than x up there, I will have to use the chain rule on e. All right, so product rule first. 250x, right, first function, times the derivative of the second. So the e term derivative is derivative of e is itself. So we write down the exact same expression, e raised to the negative 0025. But we're not done yet, right? That's just the e part, the outside. We've got to remember times the derivative of the inside. So times that negative 0025x derivative, which is just that constant decimal. All right, so first derivative of the second plus the second, which is the e term, times the derivative of the first, so times the derivative of 250x, which is just 250. All right, so there's my derivative. All right, 250x e to the negative exponent times that negative exponent plus e times 250. All right, I know I'm going to eventually solve for my critical, so I'm going to simplify before I get to the 0 step. All right, I can pull out a 250. I have 250 in each term, and I have an e term in both. And again, that will always happen with the product rule and an e term. So I'm going to factor those out. So 250 is going to be pulled out to the front. That e term is going to be pulled out to the front. And then it's times what's left over. All right, so what's left over in the first term, don't forget I have that x and that negative decimal. So in the first term, I'm left with that negative 0.0025 times x. In the second term, I pulled everything out. But remember, factoring out means dividing. So if I divide everything out, I'm still left with a 1. Right? There's still a 1 left over when I go, because if I wanted to multiply back, I'd have to have that 1 there to get the term back. All right, so there's my simplified derivative, and now my next step is to solve for the critical. The 0 case is the only case that applies, because the exponential exists everywhere, the polynomial part exists everywhere. All right, so the 0 case is the only one where I can find a critical. All right, remember, we talked about this before we went on break, exponentials are never 0. So the only place I can get a 0 is the polynomial. All right, and so that's the only part I can solve for a 0. And so I'm going to go ahead and solve. I'm going to move 1 to the other side. So I got that negative 0.0025x equals negative 1. Divide by that decimal. Oops, too many zeros. All over, that decimal. All right, then that simplifies. If you take 1 divided by 0.0025, you're going to get 400. All right, so there's my critical. All right, lands in my domain, right? 400 is between 800 and 0. All right, now since it's the closed case, I use the extreme value theorem, which guarantees I'm going to get both a max and a min on my domain, since it's a closed domain. All right, we do that by taking our critical value and our inputs and plugging them back into the original. Remember, we go back to the original revenue function, so the one that's up here. So I'm going to plug 400 in, my critical value. I'm going to plug 0 in, my endpoint. And I'm going to plug 800 in, my other endpoint. The extreme value theorem states one of those will give me my best revenue, my maximum revenue. One of those will give me my smallest revenue on my domain. Alright, so when we plug in 400 back into, again, my original revenue equation, it comes out 36,787 and 94 cents and change. 0 is going to give me 0, which again should make sense. If I don't sell anything, I don't make anything, so 0 revenue if 0 items are sold. And then 800 is my other one, so when I plug 800 in, it comes out $27,067 and about 5 cents and change. Okay, that's the one we want, right? That's my maximum. Right, that's my minimum, right? Because again, I'm guaranteed both. I didn't really need my minimum, but I found it. All right, if I don't sell any, I don't make any revenue, so that's my minimum. All right, my maximum is my critical value, and so now writing my answer. All right, so there's my test, and so the answer is they need to sell 400 items to maximize revenue at $36,787.94 and change. All right, so again, sell 400 items, they're going to make that much revenue. All right, then the last question, part C, is, well, what's going to make this happen, right? I want to find the perfect price, right? I want to find the price that will have a demand of 400, right? Because I need to have 400 items to sell in order to achieve the optimum revenue. And so I have to go back to the price equation that was given in the problem. So the 250 times the e term. So there's no x here. So it's just 250, 0, 0, negative, got my negative, 25x. And we're going to plug in the 400 into that. So to find my price, I take my, again, price revenue equation. Not revenue, price equation. And plug in x. Alright, I'm going to round to the penny. since it's dollars. And so when you plug in 400 into the price demand equation, it should come out $91.97. All right, and so that's the price that I need to set so that I will have a demand of 400 items. If I have a demand of 400 items, revenues maximum will be achieved at the $36,787.94. All right, so price is $91.97. We're going to sell 400 items at that price, and we're going to optimize our revenue. All right, so that finishes up the first application problem. Now on to the second one in the set of notes. And so the second one's asking for, so we've got the cost to produce X items is given by that cost equation, which involves e to the x times the natural log of 2x. We want to find the marginal cost function. All right, so remember, marginal cost is a special application of the derivative. All right, so I need my derivative, all right, which is going to require my chain rule and my product, or my chain rule because of the natural log of 2x, and my product rule because it's e times that natural log of 2x. And so product rule first, it's the e to the x, first function, times the derivative of the second. The second function is going to require my chain rule on the log. All right, remember, the derivative of the logarithm is 1 over the function inside, so 1 over 2x, times the derivative of the inside function, which is 2, so times 2. All right, so there's the first, the derivative of the second, plus the second, which is the natural log of 2x, times the derivative of the first. But remember, when it's just e to the x, the derivative is just e to the x, so it's itself. All right, I am going to clean it up. It's just always a good rule of thumb to do it, so I'm going to simplify. I can pull an e to the x out. All right, when I factor out e to the x, what I'm left with, so I'm pulling out e to the x, and so in this first term, I can reduce, right? This 2 reduces with this 2 and leaves me with 1 over x. In the second term, I pulled the e out, so all I'm left with is the logarithm. All right, and so there's my simplified marginal cost function, which I didn't ask you to use it, but you should know how. All right, it will find the approximate additional cost to produce the next item, so the x plus 1 item. So if they were producing 100 items, we plug 100 into the marginal cost equation, and that value would tell us how much more cost we would have about, it's an approximate, how much more cost we'd have to produce the 101st. All right, so again, make sure you do know how to do marginal analysis. All right, the next question. All right, so the font on this one's a little small, and so you're just going to have to bear with it. So hopefully you have a copy there in front of you, and you can see it a little better. For some reason, I couldn't make this one any bigger on the program that I'm using. All right, but I'll walk you through it, and I'll talk about it. All right, so we've got televisions. All right, the equation, what we're given is the monthly demand, so that's the demand equation for Blu-ray players after T months. All right, so the demand is in Blu-rays, so this is Blu-ray players. Time is in months. And we're asked to fill in the following. So A is asking, what's the demand after 8 months? So that's just a plug in my time into my demand equation. All right, so find the demand at 8. So again, just take your calculator out, plug in, and just make sure you're careful when you plug it in to the exponent. So make sure you're careful with that. And then whenever we have applications, your answers have context, they have meaning. So you should always write your answer in terms of what it's telling you. So with units, always include units for applications. And so this is Blu-ray players, and so I'm going to round, first of all, I'm going to round to the whole number because I don't want a fraction of a player. I'm going to round to the whole number. So it comes out 2143.6. So I'm going to round just correctly. I'm going to round up to 2,144 Blu-ray players. All right. Units. Always include units. You don't want to lose points on the test, homework, or the final for not including units. Always include units. All right, part B. In what month? So we want to find the time, right? In what month is the demand 3,300? And so I want to take my demand equation, set it equal to 3,300, and solve for time. All right, so again, this is just algebra. So I'm going to take this equation, 4,000 minus our 3,000 e to the negative 0.06t, set it equal to our goal, which is 3,000, and then solve. So we practiced these way back in, when we started exponentials and logarithms. So we want to isolate the e term. So first thing you do is subtract the 4,000, and so you're left with the 3,000 e to that negative 0.6t equals negative 700, and then divide out the 3,000. All right, now in this next step, make sure you're careful. Leave this fraction exact. No rounding. You can read that. No rounding. All right, so you can simplify it. I will. It simplifies to 7 over 30. And the reason why, if you round, you're going to be significantly off, because my next step is to take a logarithm, right? I want to get rid of the e. I want to isolate the t, and so I have to take the natural log of both sides, and so I have to take the natural log of that fraction. So if you round it, you'll be wrong. Your answer will be significantly off. So leave all fractions exact. Do not round until the end of the problem. Alright, so over here, our goal was to get rid of the e, which we will. That simplifies to 0.6 times time equals that natural log of 7 over 30. And then divide by the negative 0.06. Alright, so this is what we're going to plug into the calculator. That's a 6. Alright, so the time. And this one I'm probably going to round a couple decimal places. We can have a fraction of time. I can't have a fraction of a player, but I can have a fraction of time. So I'm just going to round this one a couple of decimal places. So 24.25, again, units. It's in hour, or not hours, months. It's in months. So about 24.25 months, we'll reach a demand of 3,300 players. Alright, so again, make sure units are included. Alright, part C. So I'm going to erase this over here. So part C is asking for how fast, which means a rate of change, right? How fast is a speed? So it's asking for how fast was the monthly demand changing after a year. Alright, so how fast means I want the derivative. Alright, 1 year, well remember time is in months, and so we're going to plug in 24, or not 24, that'd be 2 years. We're going to plug in 12. Alright, 12 months is equivalent to 1 year. Remember, my time is in months. When I set up my demand equation was in months. So I'm going to write it here so we have it to look at when I go to find my derivative. Alright, so there's my demand. Alright, I want to find the derivative of that and set it and then plug my 12 months in too. Alright, so the derivative first. So first the 4,000 zeros out, so then I'm left with the negative 300e. And so first thing you do is you take the derivative of the exponential, write down the exponential exactly. So negative 3,000 e to that negative 0.6 times time, but I'm not done yet. That's just the e part. Times the derivative of the inside, so it's going to be times that 0.06. And I'm going to clean this up. I can multiply the 0.06 times the 3,000, and when I do, that comes out to be 180 e to the negative 0.6 times time. Alright, so there is my derivative. And now we plug in our time. Remember, I'm plugging in 12, not 1, because 1 is a year. If I plugged 1 in, I'd only find the first month. I don't want the first month. I want 12 months later. I want a year. Alright, so I'm plugging that into the exponential derivative. And again, I'm going to round to the whole player. It comes out to 87.6, so I'm going to round to 88. Alright, the units on this means it's increasing. How fast? Well, it increases, right? Its speed is moving up by 88 players sold per month, right? Per month is its rates, right? It's change in players per month. And so remember, you have to do the units, all right? So player sold, Blu-ray player sold per month, if you want to be more precise. Blu-ray player sold per month. All right, that would be the units on it, and it's increasing because it's positive. All right, the last one for this particular application is asking us to calculate the average rate of change. So average rate of change we haven't talked about in a while. All right, average rate of change was something we talked about well at the beginning of the semester. But a lot of times this is where we like to ask on tests and the final for average rate of change. All right, so remember, average rate of change has nothing to do with the derivative function. All right, now the derivative is used, we take the limit of the average rate of change to find the derivative, but the average rate of change is the change in the function, so change in my d of t, over the change in time, and change of the variable time. And so our change in time is over the months 20 to 30 months. So we usually start with the bigger number first, so we'll take 30 minus 20, that's the change in time, and we find the demand that goes with it. So the demand at 30 minus the demand at 20. There is no derivative involved. It's the original demand equation that I'm going to use to find the demand at 30 and subtract away the demand at 20, all over the change in time. All right, so the change in time is the 10 months from 20 to 30. All right, so to find this, all right, divide by 10, right? 30 minus 20 is going to give me 10. And then I'm going to plug 30 into the demand equation and 20 into and I'm going to round to the whole Blu-ray player. So I'm going to plug those in. And so when I plug in 30 into the original demand equation, it comes out 3,504. When I plug in 20, it comes out 3,096. And then simplify, and again I'm going to round to the whole number. All right, when I round, it rounds to 41, and so remember, that's not the answer. The answer should always be units. So on average, the sale or demand is increasing, right, by 41 Blu-ray players per month. Alright, so Blu-ray players per month over those 10 months. And again, those specific 10 months, if I picked a different 10 months, I'd get a different average rate of change. So again, average rate. You don't use the derivative function at all. You just use the original function. You take the change in the original function divided by the change in time. All right, it's the slope of a secant line. All right, that's what the average rate of change is. All right, next example. All right, so the next example is actually one that's very similar to the types that you will most likely see on the final exam. So we've got our broadband internet. All right, again, this is what we're using here. The platform we're using is YouTube. All right, it's been expanding exponentially for years. All right, and so they did a study between 2007 and 2013, all right, where it estimates the number of online viewers in the millions. So I've got to keep in track that it's in millions when I go to my units. We're starting in 2007, so 2007 would be my time 0. Up to 2000, so my domain is only from 0 to 6. I don't go past 6. Be sure to label all your answers with appropriate units. Give your final answers in the spaces provided. Right, so again, this is similar to the type of question we'll ask on a test or a final. All right, just be wary of always include units. All right, so first, estimate the total. Estimate to the whole number, so I've got to remember to round to the whole number, of online videos in 2010. So 2010 would be 3 years after 2007. So I'm going to plug 3 into my, and I'm going to write my equation over here so it's a little bigger. Alright, so I'm going to find n of 3. Alright, and again, round to the whole number because they told me to. So when I plug 3 in, it comes out 166.55, and so I'm going to round to 167. Units on it would be millions of viewers. All right, millions of viewers. video viewers, all right? So it's in millions of viewers, so make sure you include that. It's important, right? 167 online viewers is a lot different than 167 million online viewers, so make sure you include units. All right, so now we're going to find the derivative, and we also want to include the units on that. So the derivative, remember, it's the exponential. I'm going to use my chain rule. It's 135e to the 0.07 times time. So the first thing you write down is the original expression, 135e to the 0.07 times time, and then multiply, so not done yet, don't forget to multiply by the derivative of the inside, which is 0.07, and I'm going to simplify that. I can take my 0.07 times my 35, and so that comes out to 9.45 e to the 0.07 times time. All right, and there's my derivative expression. All right, the units on the derivative, remember it's the rate of change, so it's a speed like miles per hour, but it would be the units of the function per the units of whatever you're plugging in. And so in this case, it would be millions, right, it's in millions, of viewers per year. It's the rate at which the millions of viewers per year is changing. Right? So the per year is what students often forget. All right, so remember the rate of change. All right, the next question is then asking you to use it. Once you find your derivative, now we're going to use it at what rate? So we're looking for a rate of change. Was it changing in 2010, which remember is 3 years after 2007, so we use 3, round your answer to the whole number. All right, so it's just taking that derivative equation and plugging 3 into it. Again, round to the whole number, so it comes out 11.67, so round to 12. So 12 million, right, units, viewers per year is how fast it's growing in 2010, right? That's the speed of growth. 12 million viewers per year. All right, the next question. In what year? So in what year, so we're looking for time, right? In what year was the number of online video viewers increasing at a rate? Round your answer to the nearest no. So we're given a rate, right, which means we want to find the time that the derivative equals that 12.5. So we want to set our derivative equation equal to 12.5. So I'm going to write my derivative equation over here. So the derivative equation was 9.45 e to the 0.07 times time. And I want to know when it equals 12.5. Alright, so I'm going to take 12.5, set it equal to the 9.45 e to the 0.07 times time, and then solve for time. So just like before, we isolate the exponential function. Alright, so the first thing I'm going to do is divide by that 9.45. So over here we've got 12.5 divided by 9.45. Now if you want to simplify that fraction, you can. I'm going to leave it. Remember, I said this earlier, we don't ever want to round the fractions. Alright, so I'm just going to leave it. If you round, you'll be significantly off because my next step is to take the natural log. Because again, I want to get rid of the e to solve for time. And so I'm just going to leave it. If you want to type that in your calculator and write a better looking fraction, you can. I'm not. I'm just going to leave it. But don't round. Biggest thing is do not round. Alright. Last step, isolate the time. So take that ugly logarithm and divide by our 0.07. So time, what you're going to plug into the calculator is the natural log of that fraction, 12.5, divided by the 9.45. Type it in exactly. And then once you type that in, you're going to divide by our 0.07 and then round to the whole number. Right, so it comes out to 3.99, so round to 4. So 4 years after 2007, so in 2011. I would accept either one of those answers. In what year? Well, 4 years after the start of our study. All right, so 4 years after 2007, that would work. Or you could just write 4 years after 2007 is 2011. All right, so either one of those answers will be acceptable. All right, the next one. Average rate of change again. All right, so I'm going to write down my original equation because that's what I have to use when I'm finding average rate. So the original equation was 135 e to the 0.07 times time. I want my average rate from 2010 to 2013. So 2010 was 3 years into the study. 2013 was 6 years, right? Because we started in 2007. And so I want to know what was the average rate the videos were increasing between 2010 and 2013. And so average rate means the change in my function over the change in time. You can read that. Good luck. All right, so the change in my function would be going from n of t. All right, so we take the function, the original, plug 6 into it, we take the function, plug 3, and then we're going to divide by the change in time. So the change in time is we're going from 3 to 6. So again, be consistent. You could flip this around. Just make sure if you pick 3 first, you're consistent with it. All right, we're going to find these values by plugging them into the original function. All right, now I'm going to round a couple decimal places when I do plug them in. So when I plug in 6, it comes out 205.46. When I plug in 3, it was 166.55. 6 minus 3, so I divide by 3. All right, that's the change in time. It's 3 years from 2010 to 2013 that I'm looking at. All right, so it comes out 12.97, so I'm going to round that to 13. And again, don't leave your answer 13. It has context. On average, the rate was increasing, right, because it's positive, by about, since I rounded, 13 million viewers per year, right? That's how fast it's changing per year on average, all right? So again, between 2010 to 2013, on average, the online viewers are increasing at a rate of 13 million viewers per year. All right, we'll stop there. We'll do the more on exponential decay models in the next set. All right, so that'll be my next video I post. So again, bear with this, guys. This is new to me, so this is a new system. I'm working with the sound. Sometimes things happen, so hopefully it works for you. You can always rewatch it and see. And so this is sort of where we are at this point. All right, so we're going to stop there.